The forgotten science of stored energy in the modern world. Energy storage usually means batteries, lithium cells, rare metals, complex chemistry, and limited lifespans. We accept degradation as normal. We expect replacement. We assume this is simply the cost of progress. But less than 2 centuries ago, engineers solved the same problem using a very different approach. They stored energy without chemistry, without electronics, without materials that degraded over time. And many of their systems still exist today, not as ruins, not as theories, but as working structures. The idea that energy storage requires batteries is a modern assumption. In the 19th century, energy storage was mechanical, gravitational, hydraulic, pneumatic, and thermal. These systems were not experimental. They were industrial infrastructure built to operate daily for decades, often for more than a century. What makes these systems remarkable is not just that they worked, it's that they kept working. While modern storage technologies are designed around limited lifespans, 19th century systems were built for permanence. Their designers expected them to outlive the people who built them. And many did. The fundamental principle was simple. Energy does not need to be stored chemically. It can be stored as position, pressure, motion, or heat. Gravity becomes a battery. Mass becomes a capacitor. Momentum becomes a stabilizer. Heat becomes stored potential. And unlike chemical batteries, these systems did not degrade just by existing. They obeyed physics, not chemistry, which means as long as materials remained intact, the energy system remained viable. This is not speculation. The evidence still stands in brick, stone, iron, and steel across Europe and North America. The question is not whether these systems worked. The question is why we stopped using them. To understand that, we must begin with the simplest and most visible form of mechanical energy storage ever created, the water tower. Gravity as a battery. Water towers and hydraulic storage. A water tower is one of the purest energy storage devices ever built. He contains no moving parts during storage. No electronics. No chemical reactions. Just mass and gravity. The concept is simple. Use energy to lift water upward, store it at height, release it later through controlled flow. This converts energy into gravitational potential energy. When released, that energy becomes pressure and motion. In the 19th century, this idea was implemented at massive scale. The Colchester Water Tower in England, completed in 1883, stood 43 meters tall and held nearly 1 million liters of water. Its purpose was to provide constant pressure to the city's water system. But functionally, it was an energy storage device. Pumping water into the tower required energy, usually from steam engines or wind-driven pumps. That energy was stored in the elevated mass of water. When citizens opened taps or when fire suppression systems engaged, gravity released that energy instantly. The system operated continuously for 104 years using the same tank. No degradation. No chemical decay. No replacement of the main storage structure. A modern lithium battery might last 8 to 12 years under ideal conditions. The Colchester Tower lasted a century. Efficiency was not perfect. Roughly 60 to 70% of the energy used to pump the water could be recovered. But what it lacked in efficiency, it made up for in longevity, safety, and reliability. When something went wrong, nothing exploded. No toxic materials leaked. The failure mode was simple. Water stopped flowing. And water towers were only the beginning. Engineers quickly realized that gravity could be used not just to store water, but to stabilize entire industrial systems. That insight led to the next major storage technology. Flywheels, compressed air, and the art of estimation. Before electricity stabilized machines, momentum did. Factories in the 1800s were powered by steam engines that produced uneven power. Machines engaged and disengaged constantly. Without regulation, this would destroy equipment. The solution was the flywheel. Massive cast iron discs, sometimes over 5 meters in diameter and weighing more than 10 tons, were attached to rotating shafts. Once spinning, their inertia resisted sudden changes in speed. When demand increased, the flywheel released energy. When demand dropped, it absorbed excess energy. This is mechanical energy storage through angular momentum. The flywheel at Quarrybank Mill in England, installed in 1820, ran for nearly 140 years. It still spins smoothly today. No battery. No electronics. Just mass, motion, and precision engineering. At the same time, cities began storing energy in another form: compressed air. Paris built the largest pneumatic energy system in the world in 1881. Steam engines compressed air at night when coal was cheap and demand was low. That air was stored in massive tanks and underground pipes. During the day, it powered elevators, clocks, factory tools, and ventilation systems across the city. At its peak, over 10,000 machines ran on compressed air, 50 kilometers of piping distributed energy. The system operated for decades. Compressed air storage was inefficient. Only about 30 to 40% of energy was recovered, but it was safe, reliable, and easy to maintain. No fires, no explosions, no chemical breakdown. Many of the pipes from that system still exist under Paris today. The lesson was clear. Energy does not need to be stored electrically to be useful. And when engineers wanted more power, they turned to something even more robust. Hydraulics, tides, and the power of massive compressed air was flexible. Hydraulic systems were unstoppable. Hydraulic accumulators stored energy by lifting enormous weights using pressurized fluid. When pressure was needed, gravity pushed the weight back down, forcing fluid through machinery at constant pressure. London's hydraulic power network ran from 1884 to 1977. It powered elevators, dock cranes, bridge mechanisms, factory presses. The accumulator at Tower Bridge used two pistons weighing 120 tons each. Together, they stored enough energy to lift the entire bridge structure repeatedly for over 80 years. The system still exists today. And long before hydraulic accumulators, engineers were already storing energy using water itself. Tidal mills stored energy by trapping water at high tide and releasing it at low tide. Some of these systems operated continuously for 700 years. The Woodbridge Tidal Mill in England, first built in the 12th century, still functions today using the same reservoir design. That reservoir is a battery. No wires, no fuel, no degradation. The same principle applies to mill ponds, dams, and later hydroelectric storage systems. Even today, pumped hydroelectric storage remains the most efficient large-scale energy storage system on Earth. Modern engineers consider it cutting edge. Medieval builders were already using it. Time, heat, and the final LESSON. Some of the most elegant energy storage systems were also the simplest. Clock towers stored energy using descending weights. Springs stored energy through elastic tension. Masonry heaters stored energy as heat. Big Ben has been running on gravity since 1859. Its weights descend a few meters per week. They are rewound by hand. They have powered the same mechanism for over 160 years. No battery has ever matched that lifespan. In homes across Europe, masonry heaters stored heat in tons of brick and stone. A single fire burned for 2 hours could heat a house for an entire day. The thermal mass acted as a battery. And like all the other systems, no chemical degradation, no rare materials, no electronic failure, lifespans measured in generations. This brings us to the final realization. The engineers of the 19th century were not less advanced. They were optimized for durability, not convenience. For repairability, not replacement. For physics, not chemistry. Their systems still exist because they were designed to last. Today, as we struggle with energy storage, grid instability, and battery degradation, these forgotten technologies offer an important reminder. We already solved many of these problems. Not with algorithms, not with rare metals, but with gravity, mass, pressure, and time. The future of energy may not require inventing something new. It may simply require remembering what already worked.